we'll eventually get something called electric potential, which actually would be a horizontal line.
Would it be like the reverse of that graph?
What do you mean by reverse of this?
Basically like going like R squared up,
Oh, curved?
yeah.
No, but you are closer. So in the dead center, so this thing is surrounded by charges here, so let me just draw an absolutely spectacular sphere. And so let each of these dots be some positive charge, excess positive charge, or excess negative charge, really does not matter a whole lot. Let's assume positive charge just for the sake of discussion. And just draw until you get tired. And I'm talking smack dab right there in the middle. What is the direction of the electric field in the center because of this charge right here?
Towards the center.
So because of this charge right here, what is the direction of the electric field at the center?
Yeah, towards the center.
I'm not quite sure how to draw that.
Wouldn't it be
At
out
the
towards
center.
towards the outside?
Which way?
From that dot, it would be going like that, right? 'Cause
Yeah.
that was going.
We assume it's all positive charges, and so electric field goes away from positive charges. So this charge right here would cause an electric field going in that direction right there. What about this charge right here? Which way is the electric field at the center because of this charge?
The other direction.
If it's uniformly distributed, then for every charge I have on one side, I'm going to have one on the other side. So ultimately, the electric field at the center, if I add up for all the charges,
So it'd basically be like static equilibrium.
what, proper analogy. So what is the total electric field?
0.
Yes. So at the center, it is 0. Down here. The question is, what happens as we get farther and farther out? And we actually derived this in the first semester course for gravitational field, or for gravitational force. And it's actually linear. And so looking at the electric field here, if I just gave you the two charts, you should have some pretty good sense. This has all the excess charge on the surface. This is even distribution throughout. Now, if I ignore the even distribution, I could set up a something other than a straight line here, but I'll save that for the test. All right, questions to hear?
Can you explain again how we got
The straight line?
Yeah.
All right, let's just go ahead and do it. I was going back and forth whether to derive it or not, but what the heck? We're all friends here, we can do this. So uniform charge distribution. So rho is equal to the charge divided by the volume. Matter of fact, whatever volume I pick, it's gonna have the same ratio here. I guess I should keep the E in there, just to differentiate it from mass density. And so, I'm just gonna take some distance r here, call that lowercase r. And so the charge in here, of this core right here, is just gonna be the charge density times the volume of that bit. And I'll put a little subscript r there to indicate we're not talking about the total volume. Q sub r. So I'm letting Q be the charge of the entire thing, this plain old V right here being the volume of the whole thing, but the subscript r is indicating I'm looking at the much smaller sphere. And the volume of this smaller sphere here is, so that'd be rho, so E, times 4/3 pi little r cubed. That's the volume of the sphere. I know the total charge density is equal to Q over 4/3 pi R1 cubed. Capital R1 cubed. Oh, who got? Now, if I am looking at this point right here, the electric field contribution from everything outside of it is 0. The only electric field the only reason there's an electric field here that's not 0 is that which is closer to the center. So the electric field, and since I'm outside this sphere here, or at the surface, I can treat that like a point charge. So this is equal to K times Q sub R over little r squared, r hat. And Q sub R is the charge density times that volume of that sphere. So that's K rho sub E 4/3 pi little r cubed over little r squared. That's the charge inside that sphere, which is K times 4/3 pi r times rho sub E. I know what rho sub E is because I know what the total charge on the sphere is, and I know what the radius of the whole thing. So this is K 4/3 pi little r times big Q over 4/3 pi big R1 cubed. 4/3 pi goes away. And I'm left with, therefore, the electric field is the electrostatic constant times big Q over big R1 cubed times R. So basically I have a constant here times R. So that's why it's a linear relationship. And I lost my R hat, so let's bring the R hat back. Or we could use calculus, but that it's not as much fun as you would think it would be. All right, Precious, you asked the question. Is that sufficient for you?
Yes.
You sounded unsure. I guess sufficient for now?
Yeah.
Okay. I'm not trying to stop you if you have a follow-up question.
No, that's fine for now.
Okay. Any other questions at the moment? Notice when we get to the surface, if little r is equal to big R1, then that R1 is going to cancel out with that, and we're left with KQ over big R1 squared, which is basically the classic point charge formula at the surface. Okay. So that's all well and good. We've dealt with a single source of charge. So now let's go into multiple choice sources of charge. So I have some Q1 here. Let's make it more generic. I have some positive charge here. I have a negative charge here. There is an electric field being produced by each of these charges. From the positive charge, I know it goes away. Now, given the way that I've drawn this, you have an indication of how strong the electric field is by if I take a certain area here. I have a certain number of electric field lines that go through it. If I take the exact same amount of area, I have fewer electric lines going through it because they're spread apart. And yes, I could add more electric field lines, perhaps illustrated better. But in this way of denoting the electric field, the strength of the electric field is denoted by basically the density of lines. The negative charge, what do we know about the electric field and negative charges?
Go towards the center.
So we have electric field going this way. Obviously stronger the closer you get to the negative charge. So the total electric field, if I wanted to draw the electric field of the whole thing, well, let's take this point right here. I basically have two electric fields that are overlapping. And so I add them. And don't forget, they are vectors. So let's go through an example. This will also help on a lab that you're doing in probably next week. So let's make this one nanocoulomb charge right here. Make this a let's make a negative 1 nanocoulomb charge. Let's keep it simple. Something clever, 2 meters apart. And I want to know the electric field here. Let's make this point. Five meters and 1.3 meters. And what is the electric field? We'll call this point P. What is the electric field at point P? So the electric field at point P is the electric field at point P because of the positive charge, plus the electric field at point P because of the negative charge. So let's do the positive charge first. I got my 1 nanocoulomb charge right here. I go over 1.5 meters to the right, and I go down 1.3 meters. With finger gestures, what is the direction of the electric field at this point? Because of the positive charge. All right. Not straight down. So we'd like to see a number of people. Okay, remember, it goes away from positive charges, and so therefore at that point right there, it's got to be going that way, which I think most people are gesturing. Because we are dealing with a two-dimensional problem, we probably should come up with a coordinate system. Which way do you want to make the I direction? Or I hat? All right, first two people I saw said I hat to the right. And J hat? All right, so I'm down first. All right. So first off, we need to figure out the magnitude of this charge. How do we find the magnitude of this charge?
Electric field equation,
Yeah, which is?
K cubed over R squared.
All right, so the electric field at point P, because of the positive charge, notice I don't have the vector symbol over it. I should properly put the vector symbol over it and then put the absolute value signs around it, just because we use capital E for energy, and it can get a real mess if we start using capital E for two different things. All right, so the magnitude will be KQ positive over R positive squared. So 9 times 10 to the 9th times 1 times 10 to the negative 9th, divided by, how do we find R? Or R squared, either one.
Trigonometry.
That's one method, with perhaps a slightly simpler method.
Pythagorean theorem.
Yeah, so either one would work here. We could find the angle using trig, so we could find that angle, call that theta positive. And then once we know that, we can then do sine or cosine to figure out what that is. So whichever way that your brain happens to be working on the moment of a test or quiz when you're doing it. Now we don't actually have to find the value of R if we're using the Pythagorean theorem, because what we're trying to find is R squared. So somewhere around, that was 2.14. What is it?
3.94.
3.94?
R squared is,
Oh, that's right, I forgot to square it. 3.94,
yes.
so I guess a little bit under 2.
It's like 1.98.
Ah, so R is 1.98 meters, because I've made this huge. So, and ultimately, what's the magnitude of this electric field? .426 units? We don't have to have units at this point, but say it again? Yep. All right. So we have the magnitude, however, it is a vector, so we need to figure out the directions here. So the electric field at point P, because of the positive charge, is going to be, well, 251. You're breaking up vectors all the time. I got a vector here, I'm breaking it up into horizontal and vertical components. So it's going to be the magnitude times the cosine of theta, I hat, plus the magnitude times the sine of theta, j hat. So 2.2842 times the cosine of theta, which is 1.5 over 1.98. Really, we really don't have to find, I'll stick in the intermediate step. We don't have to know what the angle is. This is times the cosine of theta, I hat, plus 2.2842 sine of theta, j hat, which is 2.2842 times 1.5 over 1.98 I hat, plus 2.2842. Because they're similar triangles. The triangle that looks at the electric field is similar to, using the proper geometric term, similar to the distance triangle. And we end up with, that's roughly 3/4. So it's 1, 3, 3.23. There's no way that this is 3.23.
It's 1.72.
1.72?
Oh, that one, that's, yeah. The other one's 1.4997.
And then, even though it's not our final answer, we stick our units there. Notice I do put parentheses around the whole thing if I wanted to write the units once. If I don't write the parentheses, put the parentheses in here, then that newtons per coulomb is only associated with the second term, not the first term. All right, questions about how we got to that? Because we're about to do this very similar process for EP negative.
We can leave our answer in that format.
Yeah, I mean, ultimately, I didn't specify the final format of the ESA P, so yes, that's fine. On the lab, I think I specify one in rectangular form. All right, so now EP negative. What is the direction of the electric field at point P because of this negative charge? I wasn't sure which way you were pointing. That way? And we got that way. We got it. There seems to be overwhelming. You changed your mind?
No,
You're succumbing to peer pressure?
I am.
It is indeed in that direction, towards the negative charge. I just realized I meant to make that 1.2, but we're here now, so we're sort of stuck with it. And that's really not a whole lot better. Is this the one that writes well? So we need to figure out the magnitude first, and then we break it up. Probably the biggest mistake that I see here is that when you do KQ over R squared, what I've seen way too many times is that for the I-hat direction, they looked at this first vector and they said, well, it's 1.5 meters in the I-hat direction, so let's divide by 1.5 squared for the I-hat component. No, the math doesn't work that way. So, cast that from your mind. Much better. So I got my negative charge here. My electric field is going in that direction. This is this is 0.5 meters and 1.3 meters. So it's R squared and R.
R squared is 1.94.
1.94.
And R is 1.39.
All right. So my magnitude here, EP negative, is, let's write it slightly differently, is the magnitude of EP negative times cosine of theta I hat minus sine of theta, so this angle here is theta negative j hat. It's basically magnitude and direction. Now it's negative j hat because we said down was positive. So my magnitude here, 9 times 10 to the 9th. 1 times 10 to the negative 9th over 1.94 times cosine of theta negative, well that's the adjacent of the hypotenuse, so that's 0.5 over 1.39 I hat minus the sine, which is 1.3 over 1.39 j hat. And again, I'm not forcing this particular method. You could find theta and then just find sine theta and cosine of theta the normal way. No problem with that. So magnitude is 4 point something.
4.639.
4.639.
639.
Isn't it negative 4.639?
It's magnitude.
Oh, it's magnitude, yeah, you're right.
Yeah, the negative sign's directional, we're taking that into account right here. So that's somewhere between a half and a third, so it's like probably closer to a third, so 0.37. 16 I hat, somebody will give me a correct value in a moment. So that's pretty darn close up there, so that's about 0.9514 J hat. These numbers I made up. And now time for someone to tell me that I'm wrong.
0.5 divided by 139 is, 0.3597. And the other one is 0.9353.
And so when we distribute, somewhere around 1.6.
1.669. 4.339.
4.339.
Yes.
And then finally, for the final answer, we just add them. Somewhere around there. Again, I'm not opposed to have made a Carroll's error there, but that's what I'm getting at the moment. I assume that's close enough. All right, and there's the answer. Ta-da! And your life became just a slightly more complete. Haven't seen that.
I have a question.
Yeah, Daniel.
For the negative, why did we do, cosine minus sine?
Because I know that it's going up and to the right.
Okay.
And we said that to the right was positive, and we said down was positive, and therefore up was negative.
Okay.
And that's just because I saw Mario first and he said down positive. So, it's his fault.
Then the other one would be negative. We did that positive,
Yeah, yeah.
so it's not my fault.
There's a negative in there somewhere?
Yeah, it's the math fault.
Okay. The math people, man. No other questions at the moment? All right, so let's take a more conceptual look at it. That was just one specific case there. In this particular case, I had the two charges of equal magnitude, opposite signs. I know it goes from positive to negative, and so I could also have treated this as, you know, the electric field in the middle is just gonna be going straight across. Here, it's gonna be dominated by the positive charge, but the negative charge will start to have more influence the farther it gets away from here. And so ultimately, that was what the electric field line would look like there, and then here, and you get some nice symmetry going. You could also think of this in terms of trying to visualize what's going on here. You can think of the positive charge as a fountain, the negative charge as a drain. So the electric field gets spewed out of the fountain, then eventually goes into the drain. The stuff that's shot straight across just goes straight in. The stuff that's going this way will eventually curve into it, and so forth. So suppose I had two positive charges. Two fountains shooting out water. All right, so I'm basically getting gestures on this side. So, okay, so we got the electric field going off sort of like that. It's the stuff in the middle, which is the interesting part is.
Fields would push against each other.
They would, and so what would happen from an electric field point of view?
It repels. So
Kinda like
like
they
the
crash
field,
together?
the field lines would meet.
All right, so if I have two electric field lines in the middle, both going like this,
They would start to try to curve away from each other, right?
well, I was shooting for they would cancel, but yes, ultimately, so what the electric field line would do would. And these that are drawn right here would have a slight curve to them. The ones going out directly would just be straight out. So if I have two positive charges, that's basically what it looks like. And you can go through, and it's just, think about the problem that we just did for this one and how much fun that was. And then if you were given a problem like this to actually draw it with precise numbers, you know, that joy multiplied 100-fold as you find 100 different points. Or you write a computer program to do it for you. Now suppose I've got